Hi, my name is Fernanda Timóteo. I am a graduate research assistant at the National Institute of Technology in Brazil, and today I'll talk to you about the techno-economic and environmental assessment of extracting procyanidins from Açaí seeds. So, Brazil is the world's largest producer of Açaí, having produced 1.6 million tons of this fruit in 2019. But while the edible part of Açaí corresponds to only 5 to 15% of its weight, the seed is a waste that makes up 85% of the fruit. Therefore, 1.4 million tons of Açaí seeds are generated annually in the Brazilian Amazon, and most of this biomass is currently incinerated or inadequately landfilled without recovering any chemical compound. However, Açaí seeds are a valuable source of procyanidins that exhibit antioxidant and antimicrobial activities and several pharmacological properties. But the feasibility of commercially producing these compounds from the seeds has never been assessed. Therefore, this work aims to evaluate the techno-economic viability and the environmental impacts of producing this valuable procyanidin extract from Açaí seeds at industrial scale. This work also compares this biorefinery to the most common option, the combustion of the seeds. So, in this biorefinery, after biomass is washed, dried, and milled in the first process section, it is sent to the extraction section, where aqueous ethanol extracts the procyanidins, which are then concentrated and dried to obtain a powdered extract. Then the residual biomass is sent to cogeneration to generate heat and electricity. So with regards to the methods, process simulations were developed using the software Aspen Plus and using experimental data as input. The simulation then provides the process's mass and energy balances, which will support the equipment sizing and costing, and the economic and environmental analysis. This leads to the capital and operational expenditures and the profitability and environmental impacts indicators. So, the simulation results show that the biorefinery produces 659 kilograms per hour of procyanidin extract. This corresponds to an 83% recovery of the total extractable content of Açaí seeds, which is due to simulated losses in the extractor and spray dryer. The ethanol consumption is only 22.6 kilograms per hour because there is a 99.9% recycle in the evaporator system. However, this solvent recovery requires a heat supply of 5.42 megawatts, which leaves an electricity surplus of 5.76 megawatts to be sold to the grid. Then, with these mass and energy balances, we can size and calculate the cost of the process equipment, leading to the estimation of the fixed capital investment, which was 3 times higher for the biorefinery. The extraction section comprised more than 50% of the investment, mainly due to the high costs of the evaporators. And the resulting cash flows indicate that the extract sales leads to a much higher profitability potential for the biorefinery, which displays a net present value of $56 million and a payback time of 4.5 years. In contrast, the small electricity revenue in the combustion alternative leads to a much lower NPV of $2.2 million and a long payback time of 14 years. So, because the cash flows suggested that the extract revenue has a significant impact on the biorefinery feasibility, a sensitivity analysis was performed by varying the extract price. And this analysis shows that the biorefinery is economically viable for extract prices over $2.2 per kilogram. By last, the environmental impact assessment reveals that the CO2 emissions in the biorefinery are 13.7% lower because less biomass is burned. But ethanol emissions from the spray dryer contributes to other indicators, such as the photochemical oxidation potential. So, in conclusion, this work proposes a biorefinery that can alleviate a critical environmental problem in the Amazonian region, and it is shown to be an economically feasible approach to sustainably monetize Açaí seeds. Thank you very much.